Hi everyone, welcome to this video on application of derivatives, the particle motion. We've been talking about optimization, differentials, and now particle motion. And what I want you to realize is that these are still applications of the derivative. So when we talk about finding extrema, using the first or second derivative test, all of those things that we've been using in theory, now we're putting to work in more interesting real-life problems. So these are the objectives. They're very, very simple. So let's get started. So once again, motion along a line talks about moving an object, a particle. We're calling it a particle, but it could be any object that we're moving. And so there are three basic concepts that we are using in terms of particle motion. We have a position function, usually x of t or s of t. And this determines where the particle is located on the x-axis. So what we're doing is we're moving the particle along the x-axis because it's convenient. Any particle motion, if it's just going to move right or left, could be on any axis, but moving it along the x-axis makes this easier. Once again, it's at a given time. So remember we talked about the derivative at a point. The point in this case would be in time, at a particular time. If you take the derivative of the position function, you get the velocity function. This is f prime, and it's going to talk about determining how fast the position is changing at time t, as well as its direction, right or left. Okay. Then if you take the derivative of the velocity, you get acceleration. This is the second derivative of the position function. It determines how fast the velocity is changing. The sign indicates if the velocity is increasing or decreasing. And that brings up the calculus house, because the calculus house still applies. So if we have a function that is plus minus, increasing, decreasing, concave up, concave down, that's the function. Then when the function is increasing, this first derivative is positive. If increasing, if decreasing, it's negative. If it's concave up, it's increasing, and if it's concave down, it's decreasing. And then if we move to the second derivative, then we know that if it's concave up, the second derivative is positive. If it's concave down, the second derivative is negative. And then you can see that the first derivative would be increasing. So think about this. That still works. If you say that if the second derivative is positive, then that means that the first derivative, or the velocity, is increasing. If the second derivative is negative, then that means that the first derivative, or the velocity, is decreasing. So all this stuff still applies. So here are a few more definitions talking about particle motion. When the problem says that initially just means that the time is 0, initially. At the origin means that the position function, x of t, is at 0. It's equal to 0, the position function. At rest means that the velocity function, or the derivative of the position, is equal to 0, right? So remember that adage that we said, take the derivative, set it equal to 0, right? That's when you're determining the velocity, when the velocity is at rest. If the velocity of the particle is negative, then the particle is moving to the left. If the velocity is positive, the particle is moving to the right. Now notice that we're talking about the first derivative. Positive or negative of the first derivative tells us the direction of the particle. So here are some conclusions. When velocity and acceleration have the same signs, then whatever they're doing, moving to the right or to the left, is increasing. When velocity and acceleration have different signs, then it's increasing, but for instance, if it's going this way, but that force is going against it, it's still increasing. It's increasing at a slower rate. And then if it's moving this direction, right, but that is positive, then it's going to the left, but it's decreasing in speed, so it's decreasing in speed. Okay? If the velocity is 0, but acceleration is not, it's changing directions. I can't spell this, directions. So now looking at the speed, and remember we talked about speed is the absolute value of velocity. Speed cannot be negative, so speed is always a positive quantity. So if you look at the graph here of the velocity, this is the velocity graph. Notice that part of the velocity is positive, part of the velocity is negative. But the graph of speed, notice that the positive spot looks the same, but the negative part has now been reflected over the x-axis. So remember, it is the absolute value of the velocity. So when the velocity is positive and acceleration is positive, speed is increasing. So we remember that this is going in the same direction. If they're both in the same direction, speed is increasing. But we also know that when the velocity is negative, right, going to the left, and acceleration is the left, since it's going in the same direction, speed is also increasing. All right? When the velocity is positive and acceleration is negative, once again, the signs are opposite, then it is not increasing, it is decreasing. And when velocity is negative to the left, but acceleration is positive, the speed is decreasing. So here's our first example. These are some typical scenarios. I have the word method written here. I want you to kind of pay attention to how we solve it. But it says find the velocity and acceleration of a particle given the position function. Really, all that's asking for is first and second derivative. So the velocity, if you'll recall, is the derivative of the position function. So 3t squared minus 14t minus 14. And then the acceleration is the derivative of the velocity, so 6t minus 14. T is greater than 0 because we're talking about time. The next scenario is when you're given a function, the position function, find when it is changing direction. Find when it's changing direction. So what we need to do is we need to find where the velocity is equal to 0 and see if it changes signs on either side of that. So let's take the velocity, find the velocity. That's going to be 2 cosine 2t. If we set that equal to 0, we get cosine of 2t equals 0. 2t, the cosine of pi over 2 and 3 pi over 2 are where cosine is equal to 0. So if we multiply 3 by 1/2, we get pi over 4 and 3 pi over 4. And then we need to check the domain. And the domain of this is from 0 to, because t is time, but it's in radians. So t, let's see what do I have here, 2 pi. Okay, so now I just need to check, do the signs change on either side of these? And then I have, let's see, boop, boop, boop. On this side I have, it goes from 0 to 2 pi over here. So if I put them back in, I get, I think I picked pi over 8. And when I put pi over 8 in, the cosine of pi over 4 is positive. And then if I pick one in between, that would be negative, because that between there is in the so it's in between, and then this one is plus. So it does change signs. So find the position. T is pi over 4 and 3 pi over 4. So what was the method? We talked about methods. So find the derivative of the position function, set it equal to 0, and then double check that it changes signs on either side of it. Okay, so the next scenario would be, here's a particle that's moving along the x-axis, here is his function, A wants to know, at t equals 0, is the particle moving left or right? And explain. So what we want to do, first of all, is we want to find where the position is at t equals 0. So we put a 0 in and we get 11, which is greater than 0. So that means it's moving to the right because the position is positive. All right, and then at t equals 1, is the velocity of the particle increasing or decreasing? Explain. So first of all, we need to find the velocity. So we do. We find the derivative, which is 3t squared minus 12t plus 9. And we also want to find the acceleration, which is 6t minus 12. Okay, and we want to know what's happening at t equals 1 for the acceleration, which it is 6 times 1 minus, which is negative, right? So because acceleration is negative, that means that the velocity, remember the house, right? Velocity is decreasing. And that's why, because the acceleration is less than 0. So we're still using first, second derivative tests, and we're still using what we've been doing with derivatives all along. We're just now interpreting them according to the application that we're using. Okay, here's one more example. Now these examples are really important for you to have in your notes, because when you come to class and you get ready to work problems, you can say, oh, this is like example number 1 that she worked, and this is like number 4, so that you can go back and kind of look at them instead of, because I don't really expect you to have all of this square in your head yet. You would need to do quite a few examples before you could do that. So here's another typical. We're going to find the total distance traveled over a time interval when the particle does change direction over an interval. Okay, so what are we talking about? Well, basically what we're saying is we want to know what is happening when the particle moves. So say the particle moves here, and then it changes direction and it moves here, and then it changes directions again and moves back to here. Well, what we want to do is we want to add up all of these directions so that we get a complete total for the amount of distance traveled. Okay, so this would be really awesome if we knew that it didn't change directions and we just went from here to here. Easy. But we're not going to be able to do that. We're going to have to count them and find the position. So here's how you do it. This is the method. The first thing you do is find the velocity function and set it equal to 0. All right, so 1/3 times 3 is just 1. So t squared minus 2t minus 3 is my velocity function. And this will factor. So I'm going to factor it and set it equal to 0 at the same time. Right? And that's going to give me 2 answers. T would be -1 and 3. Now I'm going to reject the -1 because time is not negative. So we're looking at t equals 3. So let's do a sign chart real quick and see that, double check that this is a place where it changes signs. Okay? So on one side of it, remember I'm plugging it back into the velocity vector, so I've got, I'll do 0 and 4. So put in 0, that's negative. If you put in 4, that'll be 16 minus, that's still positive. So it looks like this. Okay? So from 0 to 3, it's moving left. And from 3 to 6, because that's my interval, so 6 will be the end, 3 to 6, it's moving right. So it's going some way this way, and then it's going some way that way. I need to add both of them. All right? So the next thing that I want to do is I want to set up a table, and I want to evaluate the position at each of these time intervals, so I know where the particle is. So I have x of t and t. So I have 0, that's one endpoint. I have 3, I know it changes directions at t equals 3. and my other endpoint is at 6. So I need to know where is the particle when this happens. So if you put in this into the position function, not the derivative, the position function, then the first one, if you put in 0, that's real easy. Then this one is 27 divided by 3 is 9 minus, well, that's 9, minus 9, which is plus 4, which will get me negative 5. All right, so that gets me negative 5. All right, and then if I put in 6, I end up with, I did this on my paper already, I think it was 216 divided by 3, which is 72, minus 50, which is 22. Okay, so that's where it's located. So let's draw this out because this will be a little bit easier. Right? I know it goes left first, right? It goes left. So it starts at, let's do this if we can. This is at 4, all right? And it goes left, right? I quit saying that. Left all the way to negative 5. All right, so that's what it does. It goes from 4 to negative 5. Well, from 4 to negative 5, and here's a 0, this would be 9. All right, and then from this point, it goes all the way to the right to 22. So from negative 5 to 22 is 27. So total, it travels 36 during the time interval 0 to 6. And that's it. This was a long example, but it's a really good example, and I think you should be able to at least start to get an idea of how this works. Okay, so come to class tomorrow, be prepared to work on some of these. We're going to look at some tables and graphs, and then also do some more of these analytically. And then your test is coming up too. It'll be a quiz over these 3 things. So I'll see you in class.